Hi everyone, I'm Emily Graber, and today I'll be presenting about the effects of sensorimotor synchronization on temporal discrimination in different pitch contexts. I'd also like to acknowledge and thank Lola-Marie Ferly, who did a majority of the work on this project. She did her first-year master's internship with me at EarCam from April to June. Also, the behavioral lab at INSEAD was instrumental because this is where all the data were collected. So this study is primarily about the interaction of two different types of expectations. Specifically, I'll be talking about expectations in time and expectations formed due to pitch contexts. And on top of that, what happens to the expectations when sensorimotor synchronization or tapping is added. So to review, sensorimotor synchronization is the rhythmic coordination of perception and action. For example, tapping to the beat while listening to music. Sensorimotor synchronization can enhance entrainment in the brain. It literally modulates beta power oscillations, for example. And this entrainment can lead to interesting perceptual and behavioral changes, which are usually thought to stem from enhanced or focused temporal predictions, as hypothesized by dynamic attending theory. So one study that I'd like to point to, which demonstrates these concepts, is shown here. In this experiment, the participants listened to a sequence of tones and had to make a judgment about the pitch of certain target tones, which fell on the beats aligned with these hash marks above. The other tones were distractors. So the authors found that when participants tapped to the beat, they were able to improve their judgments about the pitch of the targets. So this means that the tapping actually helped the participants focus and make a judgment about what they were hearing. Pitch can also influence time perception. Marilyn Boltz, for example, found that tempo-matched melodies were judged to unfold more slowly when they contained more contour changes, and melodies with higher pitches or increasing pitches were perceived to be faster than melodies with lower pitches or decreasing pitches. Lee Van Handel found that chosen or determined tempos were slower for melodies with more contour changes. And Lee and DeLuca found that pitch predictability coming from scale sequences actually improved temporal error detection at the end of the sequence compared to sequences with random tones. So we wondered if and how the pitch content of musical sequences would alter the perception of tempo changes, and whether sensorimotor synchronization would facilitate the perception of tempo changes regardless of pitch content. And for both of these, we think yes, pitch content that is predictable should make it easier to hear tempo changes, and sensorimotor synchronization should strengthen entrainment and temporal predictions, making the tempo changes more detectable. In order to test this, we turn to a tempo change detection paradigm similar to one in an earlier study by Chikako Fujioka and myself. Here you can see sequences that contain eventual tempo changes. There are two tempo change directions and 3 different sequence lengths so that the participants cannot easily predict when the tempo change will begin. And the main task in this paradigm is to listen to the auditory sequence and then hit spacebar or any key as soon as a tempo change is detected. In the current study, we added pitch changes to the sequences as well. So there was a steady condition, the control condition, where the same note was repeated over and over on middle C. There was also the chromatic up condition, where each note was a semitone higher than the previous note. The chromatic down condition, which was just the reverse. The predictable jump condition, where a chromatic scale down and up were interleaved, starting from the high note. And then there was a random condition where all the notes in the 2-octave range were played in a random order with a contour change on every note. So to recap, there were 2 different tempo change directions, the acceleration and deceleration, 3 sequence lengths, these 5 pitch conditions, and a sensorimotor synchronization factor. So the experiment had 2 blocks, which were presented in a counterbalanced fashion. The participants either tapped to the stimuli with their dominant hand or not, and then responded with their non-dominant hand upon detecting the tempo change. As soon as they responded to that tempo change, the sequence ended, and the participant then reported whether they detected an acceleration or deceleration. Altogether, we recorded 29 usable data sets. So here you can see the reaction time data from our control condition, the study condition. On the x-axis is the sequence length. So the accelerations are in blue and decelerations are in orange. So you can immediately see that the participants reacted more slowly to the decelerations. And I'll say more about this in a minute. Also, the solid lines are the reaction times with tapping. So it's pretty clear that the tapping makes the reaction slower. Next, I'm showing you the chromatic up pitch condition, which looks relatively similar to the steady condition. And then the last three pitch conditions have a different pattern of results. So the acceleration in blue were actually detected more slowly than the decelerations. The blue is above the orange. But like the steady and chromatic up conditions, the tapping was globally slower. The solid line is higher. So formally, we analyzed these data. They were four-way repeated measures using a linear mixed effects model with random effects for the participants and a covariate of length, because we expected that the reaction times would change with the sequence length. And you can see that's true in these plots above. But we were primarily interested in the interaction with the other factors. So the pitch condition, the direction of the tempo change, and the entrainment level, the sensorimotor synchronization. So here's a bit more detail about the reaction times for the pitch conditions, averaged across sequence length and tapping condition. So each dot represents one participant, and there are 29 dots in each cloud. What you can see is that depending on the pitch content and the direction, of the tempo change, the reaction times are actually different, which suggests that the perception and then the behavior was altered by the pitch context. So another way to think about it is that the pitch context may actually prime or cause anticipation for specific tempo changes. And whether that priming would come from long-term exposure or something else would be an interesting topic to examine in the future. But it's worth noting that there, in the cases where the pitch and tempo changes were congruent, the reaction times were the fastest. Also, in all cases, the reaction times were never the same for accelerations and decelerations, even in the steady condition, as I said earlier. And in my previous experiment, which did not manipulate pitch, I actually saw the same thing and speculated that it was due to the stimuli themselves, given that accelerations are a series of earlier and earlier beats. So the faster reaction time could simply be due to the early nature of the accelerations, but something else could also be happening here. So for example, the steady pitch context may actually prime the listener for accelerations. This could be an adaptive behavior, for example, in a situation where something like a tiger is walking and then running toward you, or maybe statistically steady pitch music tends to speed up over time. Finally, it looks like the random pitch and predictable jumping pitches are relatively similar. Looking at how accurate the participants were is also interesting. Recall that they had to report whether they heard the acceleration or deceleration for every sequence. So this time in the steady condition, the control condition, the performance was near ceiling for both types of tempo changes. So people were quite accurate at reporting the direction of the tempo change. And in fact, this was also true for the random condition. But in the cases where the pitch and tempo changes were incongruent, so that's where the chromatic scale down was with an acceleration, people were quite inaccurate. So it seems like the participants both had very slow reaction times to the tempo changes, and they weren't sure about the direction of the change. Finally, sensorimotor synchronization did not improve the reaction time. So after averaging over the pitch context, which didn't have an interaction with this factor. The tapping, which is shown here on the left, made the reaction times longer, not shorter, which is what we expected. And only the effect of tapping on the correct identification of the tempo change was a marginal interaction. So to conclude, pitch context can cause certain expectations for tempo changes. For example, a rising chromatic seems to have caused strong anticipation for acceleration. So then when an acceleration actually happens, it's very easy to detect. On the other hand, the sensorimotor synchronization did not facilitate perception, at least as measured by these reaction times. And perhaps tapping causes you to feel the groove of the music, which actually is a distraction from a more judgmental way of listening. And this might actually be a good thing, because if listeners lost track of the beat in music every time there was a little bit of rubato, then that expressivity would just lose meaning. And finally, I wonder if there's a way to use these results to understand experiences for contemporary classical music. And the reason I bring this up is that I've been investigating why many people don't like that kind of music. And one reason could be that, you know, people can't easily make predictions while listening to some types of contemporary music, maybe due to the pitch, or maybe the temporal expressions that the musicians add to the music can't really be discerned, so it makes the music seem less emotional, and then people don't like it. But the random pitch condition in the current study, which was kind of closest to the contemporary music that I'm talking about, looked somewhat similar to the predictable jumping condition and the chromatic down condition. So in other words, the random pitches didn't seem to throw people way off compared to the other data we recorded. So on that note, I'll stop, and thank you very much for your attention. And I also would like to thank the funders who made this research possible.